Right now, at the edge of a black hole, the two greatest ideas in all of science are at war. Gravity says everything that falls in is crushed and gone forever. Quantum physics says that is impossible, because information can never truly be destroyed. Both cannot be right. And you are about to see what happens when these two worlds collide. A glowing edge that leaks starlight one atom at a time, a giant black hole slowly dying in the dark, a wall of fire that might cook you alive, a secret wormhole hiding inside every pair of particles. If your mind loves being stretched to its breaking point, like and subscribe, and stay close. What we find at the bottom could mean our whole universe is a projection, a shadow of something far deeper. Take a breath. Hold on tight. We begin. A giant star is dying. For 10 million years it burned so hot that its own light held it up, pushing out against the crushing pull of its weight. Now the fuel is gone, the fire dies, and nothing is left to fight back. Gravity has been waiting. In less than 1 second, the core of the star falls inward. A ball of matter wider than the sun collapses down toward a single point. The speed is unreal. The outer layers rush in at nearly 100,000 miles per hour, then faster still. Here is the thing about gravity. It never gets tired. Every other force in nature can be stopped. Push hard enough against a wall and the wall pushes back. Squeeze the atoms in a rock and they shove away from each other, refusing to get closer. That stubborn shove is what holds up mountains, planets, and you in your chair right now. Pile on enough weight, though, and even that shove breaks. When a star more than 20 times heavier than our sun collapses, the crush becomes so strong that atoms give up. They stop pushing back. They fold into each other and keep falling, with nothing in the whole universe able to stop them. What forms is a black hole, a place where gravity has won so completely that it beats every other force combined. We call it black for a simple reason. To escape any object, you have to move faster than its escape speed. Leave Earth, and you need about 25,000 miles per hour. Leave the Sun, and you need far more. A black hole packs so much mass into so tiny a space that its escape speed climbs past the fastest thing that exists, the speed of light. Light itself, moving at 186,000 miles every second, tries to leave and falls back in. Think of it like a hill, a gentle hill, and a marble rolls right over the top, a steeper hill, and the marble needs a harder push. Now imagine a hill so steep it becomes a cliff with no top at all, a slope that curves back on itself forever. Roll the marble as hard as you want, it comes back down. A black hole is a hill in space so steep that even light cannot climb out, and light is the fastest messenger in existence. If light cannot escape, then no signal, no picture, no cry for help can ever reach us from inside. The black hole goes dark. It becomes a hole in the sky, a spot where the stars behind it simply vanish. The strangest part is how small these things are. A black hole with the mass of our entire sun would be only about 4 miles across. That is the size of a small town. Squeeze something 1,000,000 times heavier than Earth into a ball you could drive across in 5 minutes, and you get one of the darkest objects in the cosmos. Scientists have found these dark giants sitting at the center of nearly every galaxy, including our own. They are real. We have photographed the glowing gas swirling around them. We have felt their gravity bend the light of distant stars. Here is what nobody tells you at first. That dark edge, the point of no return, hides a door. And what waits just beyond it breaks the rules of physics in ways that terrified even the man who discovered them. Imagine you are falling toward a black hole, feet first, watching the darkness grow. Somewhere ahead of you is a line. You cannot see it. It gives off no light, makes no sound, has no wall or gate. Yet crossing it is the most important thing that will ever happen to you, because once you pass it, you can never come back. Scientists call this line the event horizon. It is the true edge of a black hole, the border between the universe you know and a region you can only enter. The name is perfect. An event is anything that happens, a clap, a heartbeat, a word. Beyond this line, every event you cause is trapped. No light from it, no ripple, no news of any kind can climb back out to the rest of the cosmos. You could scream the loudest scream in history, and the universe outside would hear silence. Here is the part that bends your brain. The event horizon is made of empty space, the same nothing that fills the room around you. You could cross it without even knowing. There is no bump, no flash, no warning. One moment you float in normal space. The next moment you have passed the point of no return, and the door has quietly shut behind you. Someone watching you fall from far away would see something very different, and it is one of the eeriest tricks in all of physics. Gravity slows down time. The stronger the pull, the slower the clock. This sounds made up, and yet we prove it every single day. The satellites that run the maps on your phone sit high above Earth, where gravity is weaker, so their clocks tick a tiny bit faster than clocks on the ground. Engineers have to correct for it, or your map would drift off by miles. Now push that idea to the extreme. As you fall toward the event horizon, gravity grows monstrous, and to a distant observer, your clock crawls slower and slower. They watch you approach the edge, and you appear to freeze. Your falling body slows, reddens and dims. To them, you never quite arrive. You hang at the border like a fly stuck in amber, growing fainter over millions of years until you fade from sight completely. To you, though, everything feels normal. You fall right through the horizon in an ordinary amount of time, feeling perfectly fine. Two people see the same fall, and they disagree on whether you ever crossed. Both are correct. Reality itself splits into two honest stories, depending on where you stand. The size of this door depends on the black hole. A giant one at the center of a galaxy can have an event horizon wider than our entire solar system, big enough to swallow the orbits of every planet with room to spare. Cross that edge, and you would feel calm, dark space, even as your fate is sealed, and your fate is sealed. Once inside, every path you can possibly take, every direction you can turn, leads to the same place. Forward, backward, left, right. All of them point down toward the center. Space itself has tilted so hard that the center becomes your future, as unavoidable as tomorrow. So what waits at that center? Physicists chased the math down deeper and deeper toward the middle until the numbers did something no equation is ever supposed to do. They exploded. Follow the falling astronaut all the way down, past the event horizon, toward the very center of the black hole. This is where our best science comes apart. At the middle sits something the math calls a singularity. It is the point where all the matter that fell in ends up, crushed into a space with no size at all. The numbers say the matter is squeezed into zero volume, and the density climbs to infinity. Infinity is a warning sign. In physics, when an equation spits out infinity, it usually means the equation has hit a wall and stopped making sense. A good theory gives you a number you can measure. A theory that hands you infinity is telling you it no longer knows what's going on. Albert Einstein gave us the rulebook for gravity, a set of equations that describe how mass bends space and time. For over 100 years, these equations have passed every test we throw at them. They predicted black holes before anyone found one. They predicted the bending of starlight, the slowing of clocks, ripples in space from crashing black holes that we later caught with giant detectors. The rulebook works beautifully, everywhere we look, everywhere except the singularity. Feed the center of a black hole into Einstein's equations and they scream. Gravity goes to infinity, the curving of space goes to infinity. Time as we understand it comes to an end. At that exact point, the math simply breaks, like a calculator flashing an error it cannot clear. Picture driving a car toward a cliff at night with no headlights. Einstein's equations are the road, smooth and reliable for the whole trip. Then the road ends at the edge, and past it there is only black air. The equations take you right up to the singularity and then vanish. Whatever happens at that exact point, our current science genuinely cannot tell you. Why does this matter so much? Because a singularity is nature showing us the edge of everything we know. It is a spot inside our own universe where the laws of physics, the same laws that run stars and galaxies and the screen you're watching, stop working. And that should be impossible. The universe is supposed to follow its own rules everywhere all the time. There is a clue, though, in why the equations fail. The singularity is unimaginably heavy, so gravity rules it. It is also unimaginably tiny, smaller than an atom, smaller than the tiniest speck we can measure, and the world of the tiny has its own rulebook, a completely different one called quantum physics. Here lies the trap. To understand the centre of a black hole, you need the rulebook of the huge, which is gravity, and the rulebook of the tiny, which is quantum physics, at the exact same time and in the exact same spot. Nowhere else in the universe do these two worlds meet so violently, and the two rulebooks hate each other. Ask them the same question about the singularity, and they hand you answers that flatly disagree. One says one thing, the other says the opposite, and there is no referee to settle it. For decades, physicists treated this as a distant puzzle, a place too weird to reach. Then one quiet man in a wheelchair asked a simple question about the edge of a black hole, and the answer he found lit a war between these two rulebooks that still burns today. Two rulebooks run the universe. For 100 years, they have refused to sit at the same table. The first rulebook governs the big. Einstein's theory of gravity explains planets, stars, galaxies, and the shape of space itself. In this world, everything is smooth. Space and time flow like a calm sheet, bending gently around heavy objects. Give this rulebook the position and speed of a planet, and it will tell you exactly where that planet will be 1,000 years from now. It is precise, elegant, and it treats the universe like a perfectly smooth fabric. The second rulebook governs the small. Quantum physics explains atoms, electrons, and the tiny particles that build everything you have ever touched. And this world could not be more different. Down at the smallest scale, everything jitters and flickers. Particles pop in and out of existence. A single particle can be in many places at once, only settling on one when you look. This rulebook gives you odds, like a weather forecast. 70% chance the electron is here, 30% it is there. Each rulebook is a champion. Gravity has passed every test astronomers have ever run, down to ripples in space measured smaller than the width of a proton. Quantum physics is the most tested, most successful theory in the history of science, correct to more decimal places than any idea humans have ever checked. Your phone, your computer, every glowing screen exists because quantum physics works. So we have two perfect theories, and that is the problem. They describe different kingdoms and almost never cross paths. Gravity matters for the huge and heavy. Quantum physics matters for the tiny and light. A planet is far too big to flicker like a quantum particle. An electron is far too light for its gravity to matter. Each rulebook stays in its own lane, and everyone gets along. Almost everyone. Try to force the two theories to describe the same thing at the same time, and they collapse into nonsense. Ask gravity to behave like a quantum thing, all jittery and uncertain, and the equations blow up into infinities with no meaning. The smooth fabric of space cannot flicker without tearing itself to shreds on paper. Physicists have spent lifetimes trying to blend the two rulebooks into one, and for a century every attempt has failed. Think of it like two brilliant coaches who each win every game, but whose playbooks contradict each other on every page. As long as they coach separate teams, both look like geniuses. Put them in the same locker room, coaching the same players, and the whole team falls apart. For most of the universe, this quiet standoff never causes trouble. The two coaches stay in separate buildings. But there is one place in all of creation where the tiny and the heavy are forced into the same room, where a thing is both crushingly heavy and unbelievably small. That place is a black hole. Inside a black hole, and especially at its centre, gravity is monstrous and the size is microscopic. The rulebook of the huge and the rulebook of the tiny both demand control at once. They meet head-on, and they cannot both be right. For a long time, scientists assumed this clash was locked safely away behind the event horizon, hidden where no one could ever study it. Then, in 1974, a young physicist did the math on the edge of a black hole. What he found should have been impossible. Black holes, he realized, glow. In 1974, Stephen Hawking sat down to prove something everyone already believed. He ended up proving the opposite, and it changed physics forever. Hawking was studying the edge of a black hole, that invisible line of no return. Everyone in science agreed on one thing: a black hole only grows. Stuff falls in, the black hole gets bigger, and nothing ever comes out. It was the ultimate trap, a cosmic drain that only runs one way. Hawking decided to look at the event horizon using the rulebook of the tiny quantum physics. Nobody had really mixed the two worlds there before. He expected the math to confirm what everyone knew. Instead, the numbers told him something strange. A black hole glows. It gives off a faint, steady trickle of particles, a whisper of light leaking from the darkest object in the universe. At first, he thought he had made a mistake. This broke the one rule everyone trusted. He checked the math again and again, and it held. The glow was real. Today we call it Hawking radiation, and it is one of the most famous predictions in modern science. To see where the glow comes from, you have to understand something bizarre about empty space, which is coming. For now, hold on to the shock of it. The black hole, the perfect trap, is leaking. The glow is unbelievably faint. For a black hole the size of the Sun, the radiation is colder than the coldest empty space between galaxies. A temperature just a hair above the lowest possible cold, which scientists call absolute zero. You could never spot it with your eyes. A black hole like that glows more dimly than a single candle spread across the entire galaxy. But that faint glow matters enormously. It means something is escaping. And if something is escaping, the black hole is slowly losing weight. The perfect trap has a leak, and over enough time a leak drains the tank. Here is why this discovery lit a fire under the whole field. That trickle of escaping light connects the two rulebooks that hate each other. To even calculate the glow, Hawking had to use gravity and quantum physics together, at the same edge at the same time. He forced the two enemy coaches into the same room, and for a moment they produced an answer. The answer was beautiful. It was also a trap of its own, because it opened a door to a paradox so deep that physicists are still fighting about it 50 years later. Hawking gave black holes a temperature, an actual number on a thermometer. And anything with a temperature behaves in a certain way. A hot coal glows and cools. A cup of coffee gives off heat and goes cold. Hawking showed that a black hole does the same. It glows, it gives off heat, and therefore it must cool and shrink. This turned black holes from eternal, unchanging pits into something that lives and dies. They are born when stars collapse. They grow by eating gas and stars. And now Hawking had shown they slowly fade, breath by breath, into the dark. He had discovered that the most permanent-looking objects in the universe are quietly dying. But how can anything at all escape a place whose entire purpose is to let nothing escape? The light cannot climb out of the event horizon. So where did these glowing particles actually come from? The answer hides in the emptiness itself, in the space you would swear was completely empty. Empty space is a lie. What looks like perfect nothing is actually boiling with activity, and that hidden storm is where a black hole's glow is born. Take a box and remove everything. All the air, all the light, every last particle. You would call that box empty. Quantum physics says you are wrong. Down at the tiniest scale, empty space fizzes like a shaken soda. Pairs of particles constantly flicker into being out of pure nothing, exist for the briefest flash of time, then find each other and vanish again. They pop up and wink out so fast that we can never catch a single one directly. Scientists call them virtual particles, and they appear everywhere, all the time, in every scrap of empty space, including the space inside your body right now. This sounds like a fantasy, yet we measure its effects in real experiments. Put two metal plates extremely close together in a vacuum, and this fizzing emptiness actually pushes them together with a force we can detect. The nothing is doing something. Laboratories have tested it and confirmed it. The particles always appear in pairs, like two dancers springing apart from a single point. One carries positive energy, the other carries negative energy. Normally they meet again a heartbeat later and cancel out, leaving the universe none the wiser. Nothing is gained, nothing is lost. Now bring this fizzing emptiness right up to the edge of a black hole, and everything changes. Imagine a pair of these particles flickering into existence exactly at the event horizon, that invisible line of no return. Most of the time they meet and vanish as usual. Once in a while, though, the timing goes wrong. One particle drifts just inside the horizon and falls in, swallowed forever. Its partner, born a hair on the outside, escapes into open space with nowhere to fall. The pair can never reunite. The escaped particle is now stuck being real. It flies away from the black hole as a genuine speck of light or matter. To someone watching from far away, the black hole appears to have coughed out a particle. Multiply this by countless pairs all around the horizon, and you get a steady faint glow. That glow is Hawking radiation. Here is the clever, brutal part, the piece that seals a black hole's fate. The particle that fell in carried negative energy. When it drops into the black hole, it subtracts from the black hole's total. The escaping particle carries positive energy away, energy that came, in the end, from the black hole itself. So every time the black hole glows, it pays for that glow out of its own mass. It grows a tiny bit lighter with each escaping particle. The universe keeps its books balanced, and the black hole foots the bill. Picture a giant block of ice sitting in a warm room. It looks solid and permanent, yet it is quietly giving off cold, dripping away one drop at a time, shrinking so slowly you would never notice in a single afternoon. A black hole does the same with its mass, leaking it away particle by particle into the dark. A black hole has a slow leak in its side, and the leak never stops. Given enough time, an unthinkable amount of time, the leak wins, which raises a haunting question. If a black hole keeps leaking, keeps shrinking, keeps paying out its own mass, what happens at the very end when there is almost nothing left to pay? A black hole is dying right now, slowly, quietly, one particle at a time. Give it long enough and it disappears completely. We saw how the glow works. Each escaping particle steals a sliver of the black hole's mass. One sliver is nothing, but the leak never rests. Second after second, year after year, the black hole pays out its weight into the dark. Scientists call this slow fade evaporation, the same word we use for a puddle vanishing in the sun. The catch is how outrageously slow it is for a big black hole. Take a black hole with the mass of our sun. It does glow, it does leak, it does shrink. But the time it would take to fully evaporate is a number so large it makes your head spin. Written out, it would be a 1 followed by 67 zeros in years. Hold that number up against real scale. The universe itself is only about 14 billion years old. 14 billion is a 1 followed by 9 zeros. The lifetime of a sun-sized black hole dwarfs the current age of the universe so completely that the universe, as old as it is, has barely begun the countdown. These black holes are, for all practical purposes, still brand new, and the giant black holes at the centres of galaxies last even longer, with lifetimes stretching past a 1 followed by 100 zeros in years. If a single grain of sand fell every billion years, you would build a beach the size of Earth and still not come close. So why does this matter, if it takes so absurdly long? Because it means black holes have an ending at all. They belong to time, like everything else. They are born, they feed, they age, and one day, unimaginably far in the future, they die. Here is the part that flips the whole idea around. A big black hole glows very cold and leaks very slowly. A small black hole glows hotter and leaks faster. The smaller the black hole gets, the quicker it loses mass, and the quicker it loses mass, the smaller it gets. The process feeds on itself, speeding up as it goes. Picture a bonfire slowly burning down to a small pile of coals. For hours it barely seems to change. Then, near the very end, the last small chunk of wood suddenly flares up, burns hot and fast, and is gone in minutes. A black hole ends its life in a strangely similar way, calm for almost forever, then racing toward its finish. Far in the future, long after the last star has burned out and the sky has gone dark, black holes will be nearly the only things left in the cosmos. The universe will be cold, empty and black, dotted with these silent shrinking pits. One by one, over spans of time that break the mind, they will finish evaporating, and when a black hole reaches the end, when it shrinks down toward the last tiny fraction of its mass, it does something no one expected from an object famous for swallowing everything in silence. The last moment of a black hole's life is violent, brilliant and fast, a final burst that could outshine a star. The darkest thing in the universe ends its existence in a flash of light. What does that final flash look like? And could we ever catch one lighting up the sky? The answer takes us to the smallest, most dangerous black holes of all. The smallest black holes are the most dangerous. They live fast, burn hot, and end in an explosion that would light up the sky. A black hole leaks faster as it shrinks. Push that idea to its limit. Imagine a black hole near the very end of its life, worn down over countless ages to a tiny fraction of its old self. It is now smaller than an atom, yet still holding the mass of a mountain crushed into that speck. At this size, the glow becomes ferocious. A giant black hole shines colder than deep space. This tiny one blazes hotter than the core of a star. It pours out radiation faster and faster, and every burst of radiation shrinks it more, which makes the next burst hotter still. The leak has become a landslide. In the final second, the black hole dumps the last of its enormous mass all at once. The energy released is staggering. Scientists estimate that the last flash of an evaporating black hole would carry the energy of millions of the largest bombs humans have ever built, all unleashed in an instant. From the darkest, quietest object in the universe comes a final scream of light. Picture a firework. It climbs into the sky as a small, dark, silent dot. Then, at the peak, it bursts into a blaze that fills the night. A dying black hole ends the same way, silent and invisible for almost all of its life, then exploding in a final brilliant flash. This raises an exciting possibility. Most black holes we know of are far too big and too young to be dying yet. But what if some black holes were born small? Scientists think the early universe, in the wild first moments after the Big Bang, may have squeezed pockets of matter so hard that tiny black holes formed right then, without any star involved. We call them primordial black holes. Some could have started with the mass of a mountain packed into the size of a single atom. Here is the thrilling part. A primordial black hole born with just the right small mass would be reaching the end of its life right about now, 14 billion years later. Its final explosion could be happening somewhere in the sky today. Astronomers are actually hunting for these flashes. Special telescopes scan the heavens for the exact burst of a high-energy light that a dying black hole should release. Catch one, and it would be a stunning prize. It would prove Hawking's glow is real, confirm that black holes truly die, and hand us direct proof that the two enemy rulebooks really do meet at the edge of a black hole. So far, every search has come up empty. These tiny bombs, if they exist, are rare and scattered across a vast universe. But the hunt goes on, night after night, watching for a black hole to announce its death with light. A black hole spends almost its entire existence as the ultimate symbol of silence and darkness, a place where even light gives up. Then, in its final moment, it becomes one of the brightest single flashes the universe can produce. The quietest object ends the loudest, and yet hidden inside this whole beautiful story of glowing, shrinking and dying, there is a crack. A problem so deep that Hawking's own discovery seemed to break one of the most sacred laws in all of science. When a black hole finally vanishes, something falls in and never comes back out. And that missing something should be impossible to lose. When a black hole finally evaporates and vanishes, a terrible question is left behind. Everything that ever fell in, where did it go? This is the black hole information paradox, and it kept Stephen Hawking up at night for the rest of his life. To feel why it is so scary, you first need to know what physicists mean by information. Information is the full description of a thing, what it is made of, how its pieces are arranged, how fast they move, which way they spin. A book has information in its letters, a song in its notes, and every object, a rock, a star, a person, carries a complete quantum description, a kind of hidden fingerprint that says exactly what it is, down to the last particle. Now here is a law so deep that physicists trust it more than almost anything. Information is never lost. You can scramble it, hide it, burn it, blend it, and in principle it always survives in some form. The universe never truly forgets. Burn a book, and it seems gone. Yet if you could catch every wisp of smoke, every particle of ash, every flash of light and puff of heat, and track them all with perfect care, you could in theory reverse the whole fire and read the book again. The information scattered into the smoke, messy but never destroyed. Physics says this holds true for everything, everywhere, except, it seems, for a black hole. Drop that book into a black hole and the story falls apart. The book crosses the event horizon and is gone. Fine, you think. The information is inside now. Then Hawking showed us that the black hole slowly glows away and shrinks, and eventually disappears completely. Here is the horror. Hawking's glow is pure, plain radiation. It comes out random and featureless, the same dull static no matter what fell in. The glow carries no fingerprint of the book, and when the black hole finishes evaporating, it is simply gone, and the glow is all that remains. So the book fell in, the black hole vanished, and the glow that replaced it carries none of the book's information. Follow the story to its end, and the information is truly, permanently destroyed. That should be impossible. This is a full-blown crisis, because it means one of the two great rulebooks has to be wrong. Quantum physics swears information can never be lost. Gravity, through Hawking's own math, says a black hole erases it completely. Both cannot be true. One of our perfect theories has a fatal flaw, and nobody knew which one. Picture a shredder that erases the very idea of what was written, so that no genius, no supercomputer, no god could ever rebuild the page. Nothing in the known universe is supposed to do that. A black hole seemed to be exactly that impossible machine. For years, many physicists refused to accept it. They felt sure the information had to escape somehow, hidden in the glow in a way too subtle to see. Others, including Hawking at first, argued the information was simply gone, and that quantum physics would have to bend. The stakes could not be higher. If information can vanish inside a black hole, then the future stops being tied to the past in a reliable way, and the deepest logic of physics starts to crumble. To understand why so many scientists would bet their careers that the information survives, we have to look at the unbreakable law it rests on. Why are physicists so sure information cannot be destroyed? Because the entire machinery of quantum physics is built to protect it. Down in the quantum world, everything is described by something called a wave function. Think of it as the complete story of a particle, a bundle that holds every possible thing about it. This story is the information. Quantum physics has one iron rule about how these stories change over time. They evolve smoothly and predictably, and the process can always be run backward. If you know the exact state of a system now, the rulebook lets you calculate its state in the future. It also lets you calculate its state in the past. The math works perfectly in both directions, like a movie that plays the same whether you run it forward or in reverse. This two-way street is the heart of the promise. As long as you can run the movie backward, the information always survives. The present always contains enough to rebuild the past. The universe keeps a perfect memory. Even when things look hopelessly scrambled, here is a way to feel it. Shuffle a deck of cards for an hour and the order looks completely random, yet every shuffle was a real physical motion, and if you filmed it, you could rewind and watch the deck return to its starting order. The information about the original order stayed alive the whole time, it was only hidden inside the mess. Quantum physics says the universe works the same way, always, for everything. Now you can see why the black hole paradox terrified people. A black hole seemed to snap this two-way street in half. It took a clear starting state, a book, a star, a spaceship, and turned it into featureless glow, then vanished. Try to run that movie backward, and you are stuck. The plain glow does not remember what it came from. The path from past to future became a one-way street, and quantum physics forbids one-way streets. This is why so many brilliant scientists simply refuse to believe the information was gone. To them, saying a black hole destroys information was like saying 2 + 2 could equal 5. It broke a rule so basic that if it failed, huge parts of physics would fail with it. Every prediction, every experiment, every piece of technology that relies on quantum physics rests on this promise that the universe never forgets. So the battle lines were drawn. On one side stood Hawking's black hole calculation, screaming that information dies. On the other side stood the deepest law of quantum physics, insisting that information lives forever. Each side had powerful math and brilliant defenders, and they could not both be right. For a while, the two camps mostly talked past each other, each certain the other had made some hidden mistake. The black hole sat in the middle of the argument like a locked safe, holding the answer where no one could reach it. Something had to give. Either black holes were stranger than we thought, hiding a secret way to smuggle information back out, or the most trusted rule in quantum physics had a crack in it after all. This disagreement grew so sharp and the two sides were so confident that it led to one of the most famous bets ever made between scientists. Real researchers, staking their reputations, put their beliefs about the fate of the universe on the line, and the prize for the winner was strangely wonderfully specific. In 1997, 3 of the sharpest minds in physics made a bet about black holes. The loser would have to pay up with a very unusual prize. On one side stood Stephen Hawking, joined by another physicist named Kip Thorne. Hawking believed his own calculation. He argued that when a black hole evaporates, the information falling into it is truly destroyed, gone from the universe for good. He was willing to let one of the deepest laws of quantum physics break to make room for it. On the other side stood John Preskill, a physicist who trusted the quantum rulebook above all. He insisted the information must escape somehow, hidden inside the black hole's glow in a way too subtle for Hawking's math to catch. The universe, he argued, never forgets, and it would not start with black holes. They wrote up the bet formally and signed it, the way scientists sometimes do to mark a serious disagreement with a little humour. The prize was delightfully odd. Whoever lost would buy the winner an encyclopedia, a set of books packed with information. The joke was perfect. The whole fight was about whether information can be pulled back out of a place that swallowed it, and an encyclopedia is a thing you can always look facts up in. It captured a real crisis in physics, a genuine crossroads where 2 beloved theories pointed in opposite directions. The bet became famous because everyone understood that the answer would reshape how we see reality. Either black holes could erase pieces of the universe forever, or the universe had a hidden way of protecting every scrap of information, even from the ultimate trap. For years, the bet stood unsettled. Neither side could prove the other wrong, because no one could open a black hole and check. The argument lived in equations and chalkboards, in long debates at conferences, in papers passed back and forth. The safe stayed locked. But the field kept moving. Through the late 1990s and into the 2000s, a wave of new ideas washed over theoretical physics. Researchers found surprising links between gravity and quantum physics that no one had expected, strange mathematical bridges connecting the 2 enemy rulebooks. Slowly, the balance of evidence began to tip. The new ideas pointed, more and more strongly, toward one conclusion. The information was surviving. Somehow, in a way that took decades to even partly understand, it was getting back out. The black hole worked less like a perfect shredder and more like a fiendishly good scrambler, mixing information into a mess so complete it looked destroyed, while secretly keeping every piece. As the evidence piled up, one of the 2 men in the bet started to feel the ground shift beneath his feet. The calculation he had trusted for decades, the one that made him famous, began to look like it was missing something important. And this man was the type to follow the truth wherever it led. What happened next is rare in science and beautiful to watch. One of the greatest physicists who ever lived stood up in front of the world at a major conference and admitted that he had been wrong all along. He conceded the bet, and he paid his debt in the strangest, most fitting way. The moment Stephen Hawking changed his mind became one of the most famous turnarounds in the history of science. And the reason he changed it points straight at the wild new idea that may finally solve the whole mystery. In 2004, at a big physics conference in Ireland, Stephen Hawking rolled to the front of the room to say something few great scientists ever say. He had been wrong. For 30 years, Hawking had defended his answer. Black holes destroy information, he said, and quantum physics would have to accept it. Clinging to that idea would have been easy. Yet chasing the truth mattered more to him than being right. Over those 30 years, the evidence had slowly turned against him. New mathematical tools built by many physicists working across the world kept pointing the same direction. Information falling into a black hole was surviving after all. It was leaking back out, buried in the glow, hidden so cleverly that his original math had missed it. So Hawking conceded. In front of a room full of scientists and a crowd of reporters, he announced that he now believed information does escape from black holes, The great trap, he admitted, keeps the universe's memory after all. The information comes out mangled and scrambled beyond recognition, and yet fully present. Then he paid his bet. He had wagered an encyclopedia against John Preskill, and Hawking made good on it in person. He handed Preskill a thick baseball encyclopedia, and he added a joke of his own. He said he probably should have handed over the information as ashes from a burned book, since getting a clear answer out of a black hole is so maddeningly hard. A book you can look things up in was the perfect trophy for a fight about whether lost knowledge can be recovered. The moment became legendary, and not only because a famous man admitted a mistake, it marked a turning point for the whole field. The community of physicists was moving toward a shared answer at last. The information survives. The universe keeps its memory, even against a black hole. Quantum physics had held the line, but admitting the information gets out only sharpened the real mystery. Saying it escapes is one thing. Explaining how is another thing entirely and far harder. The glow leaves the black hole looking like plain random static. How could that dull static secretly carry the perfect fingerprint of everything that ever fell in? How does the information sneak past the event horizon, the line that is supposed to let nothing out? Hawking's own concession came with no clear mechanism. The exact path the information takes out of a black hole stayed foggy. He had conceded the what. The how remained one of the deepest open questions in science. And the search for that how led physicists somewhere they never expected. To explain how information escapes a black hole, they were forced to rethink what space itself is made of. They began to suspect that everything happening inside a black hole is secretly written on its outer surface, like a message printed on a bottle that describes everything sealed within. This idea sounds absurd at first. It suggests that the inside of a black hole, its whole three-dimensional volume, could be fully described by information smeared across its flat two-dimensional edge. And if that is true for a black hole, a chilling thought follows close behind. It might be true for everything, including the room you are sitting in. This is the holographic principle, one of the strangest and most powerful ideas in modern physics. And it hints that reality itself may be nothing like what your eyes are telling you. What if the three-dimensional world around you, with all its depth and distance, is secretly a projection thrown up from a flat surface? This wild idea grew straight out of the black hole mystery. To chase how information escapes a black hole, physicists kept circling back to one haunting clue. Everything about a black hole, everything it hides and holds, seemed tied to its outer edge, the event horizon, rather than to the deep space within it. The action was on the skin, not in the guts. That felt backward. We think of a box by what it holds inside, not by the size of its walls. To make sense of it, think of a hologram, the shimmering image on a credit card or a banknote. The card is flat, a plain surface with no real depth. Tilted in the light, though, and a full three-dimensional shape seems to float above it, solid and round. Every bit of information needed to paint that floating shape is stored on the flat card. The depth you see is an illusion, conjured by data living on a surface. Physicists began to wonder if a black hole is built the same way. Its rich, three-dimensional insides might be a projection, thrown up from information printed on its flat outer edge. The inside would be the floating hologram. The surface would be the card. Then came the leap that shook everything. Why stop at black holes? What if the whole universe is a hologram? What if all the depth you see, the space across your room, the miles to the horizon, the vast gulf between the stars, is a projection of information stored on some faraway, flat boundary? The world would feel completely solid and real, and still be underneath, a shadow cast by a flat sheet of data. This is the holographic principle. It says our three-dimensional reality can be described, perfectly and completely, by information living on a two-dimensional surface, with depth itself rising up as a kind of grand illusion. If this sounds like a fever dream, here is the shock. It is serious science. The holographic principle did not come from a philosopher guessing about reality. It came from hard mathematics about black holes, and it has survived test after test in the equations. Many of the world's leading physicists treat it as a real clue about how the universe is built at its deepest level, and it points a way out of the information paradox. If everything a black hole swallows is really recorded on its surface, then the information stays within reach. It waits on the edge, ready to ride the glow back out as the black hole shrinks. Nothing is lost, because everything the black hole ate is still sitting on its skin. But a bold idea like this needs proof. Saying the universe might be a hologram is easy. Showing it, with equations that actually work, is brutally hard. Physicists needed to answer two burning questions. First, how exactly does a flat surface record everything trapped inside moment by moment as new things fall in? Second, could they ever find a real, working example where a three-dimensional world and a flat surface are proven to be the very same thing? The answers turned out to be even stranger than the questions. To see how a surface can swallow and store everything thrown at it, we start at the event horizon itself and watch what happens the instant something crosses the line. Watch the exact moment something falls into a black hole and you see the universe keeping a record. The event horizon grows just a little, and that growth is the black hole writing down what it ate. Back in the early 1970s, a young researcher named Jacob Bekenstein noticed something that most physicists had brushed aside. Every time matter fell into a black hole, its event horizon got bigger. Throw in a star and the surface expanded. Throw in a cloud of gas and it expanded again. Feeding the black hole always made its horizon grow. Bekenstein connected this to a deep idea about information and disorder. In physics, when things get mixed up and scrambled, a quantity called entropy goes up, and entropy is really a measure of hidden information, of how many ways the pieces inside could be arranged. Bekenstein made a daring claim. The surface area of a black hole, he said, is a direct measure of the information it holds. Bigger surface, more hidden information. The horizon is a ledger, and every new thing that falls in adds a line to it. At the time, this sounded crazy. Most experts thought a black hole was featureless, a simple pit with almost nothing to describe. Bekenstein was saying the opposite, that a black hole is one of the richest storehouses of information in the universe, and that all of it is tallied on the surface. Picture wet clay wrapped around a ball. Press a coin into the clay, and it leaves a mark, a record of the coin, stored right there on the surface. Press in a key, a shell, a fingerprint, and each leaves its own mark. The surface remembers everything that touched it. A black hole's event horizon behaves like that skin of clay, except it records the complete quantum fingerprint of everything that falls in, and it grows to make room for each new arrival. This solves a huge piece of the puzzle. When you drop a book into a black hole, your instinct says the book is now buried deep inside, hopelessly out of reach. Bekenstein's picture says the book's information gets stamped onto the ever-growing surface as it crosses. The record lives on the edge, in the open, on the boundary between the black hole and the rest of the universe. And because the record sits on the surface, the glow leaving that surface has a way to carry it off. As the black hole radiates and shrinks, the information printed on its skin can, in principle, leave with the light. The book stayed on the wall by the door the whole time, ready to be read on the way out. Bekenstein's idea, once mocked, became a foundation stone of modern physics. It tied together three things that had seemed unrelated: gravity, which builds the black hole; information, which describes what fell in; and heat, the glow Hawking would soon discover pouring off the surface. All three met on that thin growing edge. But saying the surface stores everything raises an obvious challenge. Exactly how much can a surface hold? A book has a certain number of letters. A hard drive has a certain number of slots. If a black hole's edge is a storehouse of information, there must be a way to count the slots, to measure how many pieces of information fit on that skin. When physicists finally counted, the number they found was so large and the storage so dense that black holes turned out to be the most information-packed objects that can possibly exist. How much information can a black hole hold? To answer that, physicists imagined chopping its surface into the tiniest squares that can exist and counting them one by one. There is a smallest meaningful size in nature, far below anything you can see or build. Scientists call it the Planck length, and it is unthinkably small. Compare an atom to the whole solar system, and that gap is nowhere near big enough. The Planck length is smaller than an atom by more than the atom is smaller than a city. It is the finest grain the universe seems to have. Now imagine tiling the surface of a black hole with squares, each one a Planck length on a side. These squares are the smallest patches of surface that can carry information. Bekenstein and Hawking worked out the rule, and it is stunningly simple. Each little square holds roughly one bit, one single piece of information, one yes or no answer. Count all the squares covering the event horizon, and you have counted the total information the black hole holds. Because the squares are so absurdly tiny, even a modest black hole fits an unbelievable number of them on its surface. A black hole the mass of the Sun, only about 4 miles across, would carry more bits on its skin than every computer, phone, book and hard drive ever made by humanity, multiplied together many times over. The number of bits is so vast that writing it out would fill libraries, all of it, packed onto a dark surface a few miles wide. Here is the part that stunned everyone. A black hole is the most information-dense object that can possibly exist. Take any region of space, any size, and there is a hard limit on how much information you can cram into it. Push in more and more, packing tighter and tighter, and at the exact moment you hit the limit, the region collapses into a black hole. Nature refuses to store information any denser than that. The black hole is the ultimate full storage drive, packed right up to the edge of what physics allows. Picture trying to fill a room with books. You stack them on shelves, then on the floor, then to the ceiling, cramming in more and more. At some point the room is completely full, and one more book simply will not fit. For information in space, the black hole is that completely full room, filled to the absolute maximum the universe permits. And notice the strangeness hiding in the rule. The information depends on the surface area, on the two-dimensional skin, even though the black hole is a three-dimensional thing. Double the surface and you double the information whatever is going on in the volume inside. This is the holographic principle showing its face in hard numbers. What looks like a three-dimensional storehouse is really book kept on a flat two-dimensional edge. Everything that falls in gets recorded on the surface. The surface can hold a staggering, near limitless amount, and the total is set by area, exactly as a hologram would demand. Yet a puzzle remained, and it was a deep one. Physicists could count the information and describe the surface, and still they could not prove, with airtight math, that a flat surface and the three-dimensional world inside it were truly the same thing. What they needed was a rock-solid example. Then a physicist named Juan Maldacena wrote down a single idea that turned the suspicions into the most tested theory in modern physics. In 1997, Juan Maldacena wrote down an idea so powerful that physicists have been building on it ever since. He found a way to prove that a flat surface and the three-dimensional world inside it can be exactly the same thing. Here is what he did. He imagined a make-believe universe, a bit different from ours, shaped in a special way that made the math clean. Inside this universe, gravity works, black holes form, and space has full three-dimensional depth. Then he looked at the flat boundary around the edge of this universe, its outer surface. On that flat boundary, he placed a completely different kind of physics, one with no gravity at all, just particles dancing on a surface, following the quantum rulebook. Two separate worlds. One is three-dimensional with gravity in the middle. The other is a flat edge with no gravity wrapped around it. Then Maldacena proved the shocking part. These two worlds are secretly the same world. Every single thing that happens in the three-dimensional interior, with all its gravity and depth, matches perfectly with something happening on the flat, gravity-free boundary. Anything that unfolds in the deep interior is written in a different language on the surface. This is the dictionary. Two universes that look nothing alike, described by two totally different sets of equations, turn out to be two ways of saying the exact same thing. One page of the dictionary is written in the language of gravity and three-dimensional space. The facing page is written in the language of flat quantum particles. Think of a movie. On the screen you see a rich three-dimensional world with distance, depth and motion. The whole thing, though, is really stored as a flat pattern of data on a disk or a chip, with no depth at all. The three-dimensional adventure and the flat data are the same movie, just read in two ways. Maldacena showed that a universe with gravity and a flat surface without it can relate to each other exactly like that. This was the proof physicists had been craving. It took the holographic principle out of the land of bold guesses and planted it in solid mathematics. In Maldacena's model, the hologram idea is simply true. The three-dimensional world with gravity really is fully encoded on its flat boundary. Two descriptions, one reality. The idea has been checked and rechecked for over 25 years in thousands of ways by thousands of researchers. Every test it passes makes physicists more confident that our own universe works on the same deep principle, that gravity and space themselves might be a projection from information living on a distant surface. And it handed scientists a magic trick for the information paradox. A black hole is a creature of gravity sitting in the three-dimensional interior. But the flat boundary that describes the same universe has no gravity and no black hole to lose anything. On the boundary, the ordinary quantum rulebook rules, and that rulebook always keeps information safe. So if the boundary keeps every piece of information, the black hole inside must keep it too. The paradox cracks open. The information survives. Maldaceno's dictionary all but guarantees it. Knowing the information gets out, though, still left the hardest question standing. What is it like to actually fall through the edge of a black hole when the surface holds a perfect copy of you and the inside pulls you down? That question leads to a wall of fire. Imagine falling into a black hole. For years, physicists assumed the crossing would be gentle, that you would drift through the event horizon feeling nothing at all. Then a new calculation suggested something horrifying. You might slam into a wall of fire. This is the firewall paradox, and it came from taking the rescued information seriously. Each step in the argument seems reasonable, and together they trap you. Information escapes a black hole, carried out in the glow, in Hawking radiation. For that to work, each particle leaving the black hole must be deeply linked to the radiation that came out before it. This linking is a quantum connection called entanglement, a bond where two particles share a single fate, so that knowing one tells you about the other. Here is the trap. Remember how the glow is born. Pairs of particles appear at the event horizon. One falls in, one escapes. For the black hole to release its information the way we think it must, the escaping particle has to be tightly entangled with the older radiation, the glow that left long ago. That same escaping particle, though, was born as one half of a pair. It is also supposed to be entangled with its partner, the particle that just fell inside the black hole. And quantum physics has an ironclad rule, coming up in a moment, that forbids one particle from being fully entangled with two different things at once. You cannot share that deepest bond three ways, so the escaping particle faces an impossible demand. To save the information, it must bond with the old radiation. To be born normally at the horizon, it must bond with its infalling partner. It cannot do both. One of the two bonds has to break. If the bond with the infalling partner breaks, there is a violent price. Snapping that connection releases a tremendous burst of energy, right at the event horizon. Do the math for every particle in the glow, and the whole horizon lights up with energy. Instead of an invisible, gentle line, the edge of the black hole becomes a blazing wall, a firewall, hot enough to burn any falling astronaut to ash the instant they arrive. This wrecks one of the most trusted ideas about black holes. Einstein's rulebook says that crossing the event horizon of a big black hole should feel like nothing, because the horizon is plain empty space, with no wall or boundary you can feel. A person falling in should sail across without noticing. The firewall idea says the opposite. It says the edge is a lethal barrier of fire. Now the two rule books are at each other's throats again. To keep quantum physics happy and save the information, you seem forced to build a firewall which shreds Einstein's smooth, gentle horizon. To keep Einstein happy and let the astronaut fall through in peace, you seem forced to break quantum physics and lose the information. Once more, both cannot be true. Picture a doorway you have walked through 1,000 times, always open air, always harmless. Then someone hands you a proof that the doorway is secretly a sheet of flame that vaporizes anyone who steps through. The math just insists the fire is there. This paradox landed like a bomb in physics. It said our two best theories cannot even agree on what happens when you cross the simplest possible line, the edge of a black hole, and at the very center of the fight sits that strange quantum rule, the one that forbids sharing the deepest bond three ways. The firewall paradox rests on one hidden assumption. It assumes someone could stand back, look at both sides of the story at once, and catch the contradiction. Take that assumption away, and the fire might vanish. This escape hatch is called black hole complementarity, and it asks you to accept something that sounds impossible. The same fall into a black hole has two completely different descriptions, and both are true, because no single person can ever witness both. From your point of view, you cross the event horizon whole and unharmed, sailing toward the center. From far away, watchers see you slow, redden, and smear across the surface, your information soaking into the glowing skin and later leaking out in the radiation. So which is it? Are you inside, falling free? Or are you outside, turned to glowing static on the surface? Complementarity gives a wild answer. Both. And the reason both can be true is that these two versions of you can never meet to compare notes. Think of it this way. The outside observer would have to wait ages watching the black hole slowly glow away to gather your information from the radiation. By the time they had it, you would be long gone, far inside, unreachable. The you inside and the you outside live in two sealed rooms with no door between them. No experiment, no messenger, no clever trick can ever put both versions in the same place to expose the clash. Here is why that matters. Quantum physics has a strict rule that you cannot copy information perfectly. You cannot make two identical quantum versions of a person or a particle. The firewall seemed to demand exactly that forbidden copy. One version inside the black hole and one version in the radiation outside, two of you. That should be illegal. Complementarity slips through the loophole. There are never two of you in the same place at the same time, seen by the same observer. Outside, watchers only ever reach the outside copy. You only ever reach the inside copy. The universe quietly keeps its rule, because it never lets anyone catch both copies together. For a while, this idea felt like a real escape from disaster. Many physicists embraced it. The two stories of your fall stay forever apart, so the contradiction never actually happens to anyone, and both Einstein's smooth horizon and quantum physics can survive. This is deeply strange to swallow. It means there is no single, observer-independent truth about whether you crossed the horizon. Reality itself depends on where you stand and what you can reach. Two honest observers can hold opposite facts about the same event, and the universe refuses to pick a winner. Complementarity almost calmed the storm. It offered a way to keep both rulebooks by keeping their stories separated, sealed off from each other so they could never argue face to face. Then came the firewall argument, and it was built to attack exactly this escape. It sharpened one particular quantum rule into a blade that complementarity could not dodge, a rule about how a single bond can be shared. The firewall crowd claimed that even a lone observer, doing careful measurements just outside the black hole, could catch the copying red-handed without ever needing to peek inside. To see how, we have to open up that rule at last. The rule that a deep bond can join only two, and never three. There is a rule in quantum physics as strict as any law in nature. The deepest bond between two particles can be shared by only two, never three. We met this bond before. Entanglement links two particles so tightly that they share a single fate. Measure one, and you instantly learn something about the other, even if it sits on the far side of the galaxy. It is the strongest connection the quantum world allows. Now here is the rule that makes it dangerous. If two particles are fully entangled with each other, then neither one can be entangled with anything else, at all. Their bond is complete. It uses up everything they have to give. A third particle trying to join is locked out. Physicists call this the monogamy of entanglement, borrowing the word we use for a partnership of exactly two. Picture two people holding hands, gripping so tightly that every finger is interlocked. Now a third person tries to hold one of those hands too. There is no room. Every finger is already taken. To grab the newcomer, one of the original two has to let go. You cannot fully hold two people at once with a single pair of hands. This simple rule is the knife at the heart of the firewall. Remember how the black hole's glow is born. A pair of particles appears at the horizon. One falls in, one escapes. Those two are entangled partners, holding hands across the edge. That bond is what makes the horizon feel smooth and empty, calm enough for an astronaut to cross without harm. For information to escape the black hole, though, there is a second demand. Each newly escaped particle must also be entangled with the older radiation, the huge cloud of glow that left long ago. It has to hold hands with the past, or the information stays trapped and lost. so the escaping particle is asked to grip two partners at once, fully. It's in falling twin on one side, the ancient radiation on the other. The monogamy rule forbids it. One grip has to break. If the grip on the ancient radiation breaks, information dies inside the black hole, and quantum physics shatters. If the grip on the infalling twin breaks, that snapped bond erupts into energy at the horizon, and the smooth edge becomes a wall of fire. Either way, something we trust gets destroyed. That is the trap, tightened to its cruelest point, and this is why the firewall could not be waved away. The argument needed no one to jump inside and compare copies. A patient observer floating just outside could, in principle, study the old radiation, then catch the new particle and measure the bonds. The monogamy rule says those measurements must clash. The contradiction shows up entirely on the outside, where complementarity offered no shelter. For a while, physics seemed truly stuck. The smartest people in the field stared at a rule so basic it felt unbreakable, and it was steering them straight into a wall of fire. Then two physicists proposed something that sounded like madness. What if the escaping particle and its infalling twin are joined by a secret tunnel through space, so that the bond and the tunnel are one and the same thing? What if entanglement itself is a bridge? That single idea would rewrite what space is made of. In 2013, two physicists, Juan Maldacena and Leonard Susskind, put forward an idea so bold it still stuns people. Entanglement, they said, is a wormhole. The strange bond between two particles is a tiny tunnel through space, joining them behind the scenes. To feel this, you need to know what a wormhole is. Back in 1935, Einstein and a colleague named Nathan Rosen found that his gravity equations allowed a shortcut through space, a bridge connecting two far apart places, fall in one mouth, come out the other, skipping the long road between. For decades this stayed a mathematical curiosity, a tunnel nobody expected to be real. That same year, Einstein helped uncover entanglement, the spooky bond that links two particles across any distance. He disliked it, calling it spooky action at a distance, because it seemed to let two particles coordinate instantly, no matter how far apart. For almost 80 years, these two discoveries sat in separate drawers. A wormhole was about gravity and bent space. Entanglement was about quantum particles and information. Nobody dreamed they were related. Maldacena and Susskind dreamed it. They proposed that every entangled pair is connected by a wormhole, an impossibly thin bridge threading through space. When two particles share that deepest bond, a tiny tunnel links them. The bond you measure, and the tunnel through space are two ways of seeing one thing. Picture two distant islands with a hidden passage bored deep beneath the ocean floor joining them out of sight. From above, the islands look completely separate with miles of water between, yet a secret tunnel connects them directly. Entanglement in this picture is that buried tunnel. Particles that look far apart are quietly joined underneath. Now watch how this melts the firewall problem. The trouble was the escaping particle needing to hold hands with two partners at once, which the monogamy rule forbids. But if the infalling twin and the escaping particle are linked by a wormhole, and the escaping particle is also linked to the old radiation, then the old radiation and the black hole interior are connected too, through the network of tunnels. The partners are all sewn into a single connected space by these bridges. The two grips stop clashing, because they are secretly the same grip routed through a tunnel. The contradiction that lit the firewall softens. There may be no wall of fire because the entanglement holding everything together is the very fabric linking inside to outside. This idea did more than patch a paradox. It hinted at something staggering about reality. If entanglement is a wormhole, then the quantum bonds between particles are threads of space itself. Connection between particles and connection through space might be one thing, wearing two masks. For now, hold on to how radical this is. A pure quantum idea, entanglement, and a pure gravity idea, a tunnel through space, turned out to be one idea. The wall between the rulebook of the tiny and the rulebook of the huge, the wall physicists had banged against for a century, suddenly looked like it might have a door in it. And if a single entangled pair is joined by a bridge, then think about everything else in the universe that is entangled. Trillions upon trillions of pairs. Each one, if this is right, joined by its own secret tunnel. Take the idea seriously for a moment. If every entangled pair hides a tiny wormhole, then the universe is stitched together by an unimaginable web of bridges. Entanglement is everywhere you look, common and constant. The The particles that make up empty space are entangled with their neighbours. The atoms in this room share faint quantum bonds. Across the whole universe, countless particles are linked, pair by pair in a vast tangle of connections. If each of those links is secretly a bridge through space, then space is threaded with more tunnels than there are stars, more than there are grains of sand on every beach on Earth. This flips our usual picture inside out. We tend to think space comes first, a big empty stage, and then particles sit in it and occasionally get entangled across the gaps. The wormhole idea suggests the opposite order. The entanglement, the web of bonds, might be what builds the stage in the first place. The bridges themselves are space. Come back to the black hole. When Hawking radiation streams away, each escaping particle stays entangled with what remains behind. Over the black hole's long life, it releases a mountain of radiation, and every piece of it holds a bond back to the interior. Picture the black hole as a spider at the centre of an enormous web, with silk threads reaching out to every particle of glow it has ever released. Those threads, in this picture, are wormholes. The inside of a black hole is tied to its distant radiation by a dense bundle of quantum bridges, a network growing thicker with every particle that leaves. Here is the beautiful payoff. This is how the information gets out without breaking any rules. The interior and the radiation are connected the whole time, through the web. As the black hole shrinks and the web reorganizes, the information encoded inside can flow out along the threads, riding the connection that was there all along. The safe had 1 million hidden passages the whole time, one for every escaping particle. Physicists have tested pieces of this in their equations, and the math holds together in ways that keep surprising them. In certain carefully built model universes, they can show that adding entanglement is the same as building a bridge, and that removing entanglement is the same as cutting space apart. Pull out enough bonds and the bridge pinches shut. Space itself tears. Picture it clearly. Cut the entanglement between two regions of space, and the space between them comes undone. The tunnel snaps. The two regions drift into separate pieces with no path between them. Connection and space are so tied together that destroying the bond destroys the road. This is one of the deepest hints in modern physics that space may be woven from something more basic rather than standing on its own. It looks more and more like something built out of a more fundamental material, and that material is quantum entanglement. But to trust any of this, physicists needed proof that information truly escapes a black hole, measured and confirmed, not merely hoped for. They needed to watch the information come out in the math and chart it, moment by moment. And when they finally drew that chart, its shape became the key to everything. To settle whether information escapes a black hole, physicists needed a graph. One line tracking a single number over the black hole's entire life, from birth to final flash. The shape of that line would reveal the answer. The number measures how tangled the radiation is with the black hole, a way of tracking where the information lives. A physicist named Don Page worked out, back in 1993, exactly how that line should look if quantum physics is right and information comes back out. Here is the story the line tells. Early on, a young black hole starts glowing. The first particles of radiation drift away, each one entangled with the black hole left behind. As more radiation escapes, this tangling grows. The line climbs. For the first half of the black hole's life, the radiation looks more and more like random, meaningless static, and the entanglement keeps rising. Then comes the turning point. Halfway through, the black hole has given away half of itself. From here on, if information is truly conserved, the line has to bend and fall. The later radiation must start carrying out the actual information, linking up with the earlier radiation, so the whole cloud of glow slowly stops looking random and starts looking like a hidden message. By the time the black hole fully evaporates, the line returns all the way to zero, and the radiation holds every scrap of information that ever fell in, scrambled but complete. This rising then falling shape is called the Page curve. It looks like a mountain. The line climbs to a peak at the halfway mark, then slides back down to the ground. That peak, that bend in the middle, is the signature of information escaping. A black hole that obeys the Page curve is a black hole that keeps the universe's memory. Now here is the problem that haunted physics for decades. When Hawking did his original calculation, using his rules for the glow, he got a line that only ever climbs. In his math, the radiation gets more and more tangled forever, right up until the black hole vanishes and the information never comes back. His line shoots up and never bends. So the two calculations flatly disagreed. Page said the line must rise and fall because quantum physics demands it. Hawking's own method said the line only rises, because that is what his equations for the glow produced. One of them had to be missing something. For years, everyone suspected Hawking's version was incomplete, that his method was too simple to capture the subtle way information sneaks out. Page's mountain-shaped curve had to be right, because the alternative was the death of quantum physics. Yet no one could derive that mountain using the tools of gravity. They could say what the answer should be, they could not show their work. That gap sat open like a wound for almost 30 years. Everyone knew the destination, nobody had the road. Then, around 2019, a handful of physicists found the missing road, and it ran straight through the strangest idea we have met yet. To make the line bend, to force Hawking's climbing curve to turn back down, they had to allow wormholes to sneak into the calculation, ghostly bridges that reshaped the whole answer. Around 2019, a small group of physicists finally forced the black hole's glow to give up its secret. They made Hawking's endlessly climbing line bend back down, and they did it by letting wormholes crawl into the math. To understand the trick, you have to know how these calculations work. When physicists compute something about a black hole using gravity, they add up every possible shape space could take. Space can bend and curve in countless ways, and the final answer blends all of them together. Usually a few simple shapes dominate, and the exotic ones stay too faint to matter. For decades, everyone added up only the obvious shapes, the ones where the black hole sits alone and space behaves normally. That gave Hawking's climbing line, the one that loses information. The breakthrough came from a wilder set of shapes that everyone had ignored. In these, hidden bridges appear in the math, tunnels linking the black hole to copies of itself, or linking it to the faraway radiation. Physicists call them replica wormholes, because they connect duplicate versions of the black hole used in the calculation. These bridges are faint, easy to overlook, and for a long time nobody thought to include them. When the new teams added these ghostly wormholes into the sum, everything changed. Early in the black hole's life, the wormholes stay quiet and the line climbs, just as Hawking found. Past the halfway point, though, the wormhole shapes suddenly take over the calculation. They grab the steering wheel, and the line bends. It turns and falls, exactly tracing the mountain-shaped Page curve that quantum physics demanded all along. For the first time, using gravity itself, physicists had shown that information escapes a black hole. The very tool that once said information dies, Hawking's own gravity math, now said the opposite, once you stopped ignoring the wormholes hiding inside it. Picture doing a giant sum on a chalkboard, adding up hundreds of terms and getting an answer that feels wrong. Then someone points out a set of terms you skipped, faint ones you assumed were zero. You add them in, and the total flips to the right answer. The replica wormholes were those skipped terms, tiny contributions that reshape the whole result once you stop leaving them out. What makes this so dizzying is where the wormholes live. These are tunnels too abstract to fly a ship through, showing up inside the calculation, in the ghostly sum over all possible spaces, as connections between separate pieces of the problem. Space, in the deepest math, seems willing to secretly connect things that look completely apart, and those secret connections carry the information out. This was a genuine turning point. After nearly 50 years, the information paradox began to feel solved. At least in these carefully built model universes, information escapes. Hawking's early answer was incomplete, and the fix came wrapped in the same idea that keeps surfacing: connection through hidden bridges, entanglement stitched into the shape of space. But the replica wormhole calculation revealed something even stranger buried inside it. To make the numbers work, physicists found that a certain region deep inside the black hole suddenly stops belonging to the black hole at all and starts belonging to the radiation far outside. A piece of the interior moved in the bookkeeping to the other side of the universe. They call these regions islands, and what they imply about the inside of a black hole borders on the unbelievable. The replica wormhole math hid a shock inside it. Deep within the black hole, a region can suddenly switch sides and start counting as part of the radiation far away. Physicists call these regions islands, and the idea sounds impossible at first. An island is a chunk of space deep inside the black hole, sometimes reaching almost to the centre. By every ordinary measure, it sits sealed behind the event horizon, cut off from the outside universe. Yet when physicists carefully track where the information lives, this inner region belongs to the distant cloud of radiation, as if it had quietly moved to the other side of everything. To find these islands, physicists look for a special surface inside the black hole, a boundary they can calculate with great care. It marks the edge of the region that has switched sides. This surface follows a precise rule that balances two things at once: the area of the surface and the entanglement across it. Because it weighs the quantum bonds and not only the shape, it is called a quantum surface, and finding it tells you exactly which part of the interior now rides with the radiation. Here is what that means, and it is wild. When you collect the radiation streaming out of a black hole, you're secretly holding a piece of the black hole's insides too, right alongside the faraway particles of glow. The island deep within counts as part of what you have gathered. Reach out to the radiation, and you have reached through the hidden connection into the heart of the black hole. Think of a book with a strange binding. You hold the book in your hands, far from any library. Yet certain pages of your book are, by some impossible trick, the very same pages sitting in a locked vault 1,000 miles away. Write on your page and the vault page changes. The island is like those shared pages. It lives inside the black hole and in your hands at the same time. This solves the deepest part of the mystery. The information that fell in escapes after all, because the interior, or the crucial part of it, has become part of the radiation. As the black hole evaporates, more and more of its inside converts into island, joining the outgoing glow. By the end, everything that was inside has become part of what escaped. The interior empties itself into the radiation, region by region, and the surface that marks the island is what makes the page curve bend. Early on there is no island, and the line climbs. Then, at the halfway point, an island appears deep inside, and its arrival flips the calculation, sending the line back down. The mountain shape comes directly from the moment a piece of the interior switches sides. This is some of the most surprising math in modern physics, and it has been checked from many directions. It says the inside of a black hole is woven into the radiation outside so tightly that parts of the interior simply are the outside, seen a different way. Which forces a staggering question. If a piece of the interior can live inside the faraway radiation, then what is the interior actually made of? Physicists began to suspect the black hole's inside is built, thread by thread, out of the entanglement it shares with the world beyond it. Here is an idea that would have sounded insane a generation ago. The inside of a black hole is built out of entanglement. Weave the quantum bonds, and the interior appears. Cut them, and it vanishes. We have been circling this thought, and now we meet it head on. The island math showed that pieces of the interior secretly belong to the faraway radiation, connected by hidden bridges. Follow that all the way, and you reach a startling conclusion. The interior might have no independent existence of its own. It could be made entirely of the entanglement between the escaping radiation and what stays behind. Think about what that means for the black hole's glow. Each pair of particles born at the horizon is entangled, one falling in, one flying out. Those bonds in this picture are the very threads that stitch the inside together. The space beyond the horizon, the region the astronaut falls through, gets its shape and its existence from the web of entanglement linking the two halves of every pair. So the interior is woven, moment by moment, from quantum connection. As long as the bonds hold, the inside is there, smooth and real, a place you can fall into. The astronaut crosses a genuine space, because the entanglement is intact and the threads are pulled tight. Now imagine cutting those bonds. Suppose you could reach the radiation and destroy its entanglement with the black hole, snipping the threads one by one. According to this idea, the interior would tear itself apart. The smooth space behind the horizon would come undone, and in its place you would find the wall of fire. The firewall, appearing exactly where the entanglement was cut. The fire is what a broken interior looks like. This ties the whole story together in a single elegant knot. A smooth, empty horizon and an intact interior mean the entanglement is whole. A firewall means the entanglement has been broken. Whether an astronaut sails through or burns depends on the state of the quantum threads that build the space they are falling into. Picture a hammock woven from rope. Pulled tight, with every strand in place, it holds a real, solid shape you can lie in. Start cutting the ropes, and the shape sags, then collapses, until nothing is left to hold you. The inside of a black hole, in this view, is a hammock woven from entanglement. The shape is real only as long as the threads are. This is a profound shift in what we mean by inside. We usually think a container has an inside no matter what, a hollow that just exists. This idea says the inside of a black hole is a construction, held up by connection, with no guaranteed existence apart from the bonds that build it. Take away the entanglement, and there is no there. Physicists find this both thrilling and unsettling. It suggests that space, at least inside a black hole, is a woven thing rather than a given thing. And if the inside of a black hole is built from entanglement, a bigger question rises up, impossible to ignore. What about everywhere else? What about the space in this room, the space between the stars, the space your own body takes up right now? If entanglement can weave the inside of a black hole, maybe it weaves all of space, everywhere. Take the boldest step of all. Maybe every bit of space in the universe, everywhere you look, is woven from entanglement. Space itself might be a fabric, and the threads are quantum bonds. For centuries, space was the ultimate given. It was the empty stage, the fixed backdrop where everything else happened. Einstein made the stage flexible, letting it bend and stretch around mass. Yet even he treated space as a real thing, a smooth sheet that exists on its own. The idea rising now goes deeper and stranger. Space may be assembled from something more basic, rather than standing on its own as the bedrock of reality. Space may be built. The clue came from black holes, but it points at the entire cosmos. Inside a black hole, the interior seemed to be woven from the entanglement between the glow and what remained. Physicists ask the obvious next question. If entanglement can build space in there, why not out here? In their model universes, they tested it, and the pattern held beautifully. Take two regions of space that are strongly entangled, and they sit close together, joined by a short, fat bridge. Weaken the entanglement between them, and the bridge stretches thin, pushing the regions apart. Cut the entanglement completely, and the bridge snaps. The two regions fall out of contact, with no space connecting them at all. Distance itself tracked the strength of the bonds every time, so the amount of entanglement between two places seems to set how far apart they are. Heavy entanglement means near. Faint entanglement means far. Zero entanglement means disconnected, torn into separate pieces. The web of quantum bonds draws the map of space, deciding what is close to what. Picture a chain-link fence made of countless tiny rings hooked together. Step back, and it looks like one smooth sheet, a solid surface. But that surface is really nothing more than the pattern of connections between the rings. Undo the links, and the sheet is gone, leaving loose rings with no shape. Space, in this picture, is the sheet. Entanglement is the linking of the rings. This idea carries a name in physics, the notion that geometry, the shape and distance of space, comes from entanglement. It remains an unproven idea, and physicists are careful to say so. In the special model universes, the math works and the picture is clear. Whether our own universe truly runs this way is still an open frontier, one of the hottest questions in all of science. If it turns out to be true, the payoff is immense. It would finally join the two rulebooks that have fought for a century. Gravity, which is really the bending of space, would come from quantum entanglement, which lives in the rulebook of the tiny. The bridge between the huge and the small would be entanglement itself. The war would end because one side was secretly built out of the other. It would also mean the solid world around you is a kind of grand illusion, in the deepest sense. The distance to the wall, the space between you and the moon, the emptiness between galaxies, all of it woven from a shimmering web of quantum threads, none of which you can see. And if space is woven from information and bonds, then a black hole becomes the most extreme knot in that fabric anywhere. Which is why physicists now study black holes as something new. The the fastest, most furious information machines the universe has ever built. A black hole is the fastest scrambler in the universe. Drop in a message, and it mixes that information into chaos quicker than any object nature allows. We have seen that a black hole keeps every scrap of information that falls in. Now look at what it does with that information while it holds it. It scrambles it, blending it so thoroughly and so fast that the message becomes impossible to read from any small piece of the glow. And the speed of this scrambling turns out to be a deep law. Start with what scrambling means. Toss a drop of ink into a glass of water. At first the ink is a clear blob, easy to see. Stir it and the ink spreads, threading through the water until it colours the whole glass evenly. The information about where the drop landed is still there, hidden in the exact position of every ink particle, and you could never read it by glancing at one corner. It has smeared across the whole glass. A black hole does this to information, with a violence and speed nothing else can match. Throw in a particle, and its information spreads across the entire black hole, blending into the rest until no small sample of the outgoing radiation reveals what you tossed in. You would have to capture almost all of the glow and untangle it with a perfect quantum computer to read the message back. Here is the astonishing part. Physicists worked out the fastest that any object in nature could possibly scramble information, a hard speed limit set by the laws of physics. Then they checked black holes against it. Black holes hit the limit exactly. They scramble as fast as the universe permits, and nothing scrambles faster. They are called fast scramblers, and they define the ceiling. How fast is that? For a black hole the size of the one at the centre of our galaxy, the time to fully scramble a piece of information is stunningly short given its enormous size, a fraction of a second by some estimates. A monster wider than many stars mixes your message into total chaos in less time than a blink. This speed looks like more than an accident. It seems tied to the deepest workings of gravity and quantum physics together. The same black holes that sit at the crossroads of the two rulebooks also happen to be the most powerful mixers of information anywhere. It hints that gravity and the spreading of quantum information are two faces of one process. Picture the world's fastest blender, one that hits the absolute physical limit of how quickly it can mix. Drop in something, and it is puree before you finish the word. No blender could ever be faster, because physics forbids it. A black hole is that ultimate blender, built for information instead of fruit, running at the maximum speed reality allows. Studying this has turned black holes into strange laboratories. By asking how they scramble, physicists probe the exact place where gravity and quantum information meet, learning rules that might apply to the whole universe. Black holes have become teachers, showing us limits we could find nowhere else. And if a black hole is the fastest information mixer allowed by nature, running right at the edge of what is possible, then it starts to look less like a pit in space and more like a machine, the most powerful computer the universe knows how to build. Think of a black hole as a computer. It holds more information in less space than anything else, and it processes that information at the fastest rate nature allows. We already saw that a black hole stores the maximum possible information for its size packed onto its surface right up to the limit physics permits, and we saw that it scrambles that information faster than any other object. Put those together, and a black hole starts to look like the ultimate machine for storing and churning through information, a computer built by gravity. Physicists have taken this seriously and asked a strange question. If a black hole is a computer, how powerful is it? They worked out the numbers using the basic laws of physics, treating the black hole as a device that flips bits, the way your phone flips ones and zeros. The answer is beyond staggering. A single black hole the mass of a large star could perform more operations every second than every computer humanity has ever built, combined by an amount so vast it defies any comparison. And its memory matches its speed. A black hole the mass of the sun stores more bits on its surface than you could record by writing on every atom in a mountain. All of that in a dark sphere a few miles wide running at the speed limit of the universe. This raises a thought that sounds like science fiction, yet falls out of plain physics. The most powerful computer that could ever exist for a given amount of matter is a black hole. Push any computer to store more and compute faster, cramming in more matter and energy, and eventually you cross a line where it collapses under its own weight into a black hole. At that point, it becomes the ultimate computer, the final form any information machine can take. Nature caps computing power, and the cap's a black hole. Picture building better and better hard drives, each one tinier and denser than the last, each holding more. You keep going, packing information tighter into less space. There is a final drive at the end of that road, the densest one allowed, and it is black and round and swallows light. Every attempt to build the perfect memory ends at the same destination. Some physicists take this further and wonder about the universe as a whole. If black holes are the ultimate computers, and if space itself is woven from information and entanglement, then maybe the entire cosmos is at bottom something like a giant computation. Every particle, every bond, every patch of space a piece of one vast process unfolding. This is a bold and unproven idea, closer to speculation than settled science, and physicists flag it clearly as such. But it grows out of hard facts about black holes. What is solid is this: black holes sit at every extreme at once. The most gravity in the least space, the most information on the least surface, the fastest scrambling nature allows, the most computing power matter can reach. They are the universe pushed to its absolute limits, all in one dark object. And when something sits at every limit at once, strange doors start to open. One of the strangest is a mirror image of a black hole, a thing that runs the whole story backward. Instead of swallowing everything, it would spit everything out and refuse to let anything in. Flip a black hole in time and you get its mirror twin. A white hole. Nothing can fall in and everything pours out. It is a black hole running backward. The idea comes straight from the math. Einstein's gravity equations do not care which way time flows. They work the same forward and backward. So if the equations allow a black hole, a place that swallows everything and lets nothing leave, they also allow the exact reverse, a place that spews everything out and lets nothing enter. Reverse every arrow, and a black hole becomes a white hole. Picture a movie of water swirling down a drain, vanishing into the dark hole at the center. That is a black hole. Now run the film backward. Water erupts up out of the drain, gushing outward, and nothing can push back down into it. That gushing, unenterable fountain is a white hole. At the edge of a white hole sits a horizon, like a black hole's, with the rule flipped. A black hole's horizon is a line you can cross going in but never coming out. A white hole's horizon is a line you can cross coming out but never going in. Try to approach one and fall inside, and you find you cannot. The exit works one way, and that way is out. So do white holes exist? Here we have to be honest. No one has ever seen one. They live for now purely in the mathematics. Black holes are real, photographed and measured many times over. White holes remain a solution to the equations with no confirmed example anywhere in the sky. They might be forbidden by some rule we do not fully understand yet, or they might be out there, waiting to be found. There is a reason to doubt they can form. A black hole is born the natural way when a heavy star collapses. Physicists have never found a natural process that would build a white hole. Making one seems to require setting up the universe in an extremely special, finely tuned state, the kind nature rarely arranges on its own. That leads many physicists to suspect white holes never actually form, even though the equations permit them. But a tantalizing idea connects them back to our story. Remember that a black hole slowly evaporates, shrinking down toward its final moment. Some physicists wonder what happens at the very end, when the black hole reaches the smallest possible size and the ordinary rules break down. Perhaps, at that instant, a black hole flips into a white hole, and everything it swallowed over its long life comes bursting back out in a final release. The trapped information would escape all at once, as a sudden fountain at the end instead of a slow leak. This is far from proven. It is one of several guesses about how a black hole truly ends, and physicists argue about it openly. But it is a beautiful possibility. It would mean nothing is ever truly kept, only borrowed and returned when the black hole dies. Even stranger ideas grow from this seed. If a white hole can gush out matter and energy, and if a black hole's collapse can flip into an outward burst, then some physicists have asked a dizzying question. What if that burst on the other side looks like the birth of a whole new universe? What if inside every black hole a cosmos is waiting to be born? Here is one of the wildest ideas in all of physics. Every black hole might give birth to a whole new universe, hidden inside it, forever out of our reach. The thought starts at the singularity, the crushed point at a black hole's center where our equations break. We usually treat that point as an ending, the place where everything that falls in is destroyed. But some physicists wonder if it is a beginning instead, a doorway rather than a dead end. Their reasoning goes like this. At the center of a black hole, matter is crushed to unimaginable density, hotter and tighter than anything else in the cosmos. That extreme state looks oddly familiar. It resembles the conditions at the very start of our own universe, in the first instant of the Big Bang, when everything we see was packed into a searing tiny point. So they ask a bold question. What if the crush at the center of a black hole bounces, instead of ending in a singularity? What if, rather than collapsing to a point and stopping, the matter rebounds and explodes outward into a brand new space of its own, a fresh Big Bang giving rise to a baby universe? That new universe would balloon out on its own side, complete with its own space and time, sealed off from ours by the black hole's horizon. If this is right, we would never see the newborn universe. It would grow in a direction we cannot point to, budding off into its own separate existence, never taking up room next to us. From our side, we would see only the black hole dark and silent, giving no hint of the cosmos blossoming within. Take this thought to its natural end, and it turns staggering. Our universe is filled with black holes, uncountable numbers of them. If each one births a universe, then reality is a sprawling family tree of cosmoses, each spawning more, branching endlessly. And here is the vertigo. Our own universe, the one holding every star you have ever seen, might itself have been born inside a black hole sitting in some parent universe, one level up. One physicist pushed this into a striking theory. He suggested that universes which are good at making black holes would, in a sense, have more offspring since each black hole is a birth. Over vast stretches of this cosmic family tree, universes tuned to produce many black holes would come to dominate. And a universe good at making black holes is also, it turns out, a universe good at making stars and the ingredients for life. It is a sweeping idea that tries to explain why our universe looks the way it does. Now for the honest part. None of this is proven. It is speculation built on the edges of what we know, a set of imaginative guesses about what hides beyond the singularity. We cannot see inside a black hole, and we cannot check whether a universe waits there. Physicists offer these ideas as possibilities worth chasing, not as established facts, and they say so plainly. Yet the very fact that serious scientists take such ideas seriously tells you something. At the center of a black hole, our understanding runs out so completely that the birth of a universe becomes a reasonable thing to wonder about. And that total breakdown, that place where every rule we trust simply stops, is the next stop on our journey. At the center of a black hole, something happens that breaks the mind. Space and time stop meaning what they always meant. The words themselves run out. We have circled the singularity many times, calling it the point where equations fail. Now go right up to it and look at what actually falls apart. It goes deeper than a broken formula. The very ideas of here and there, of before and after, seem to dissolve. Start with a strange fact about the inside of a black hole. Once you cross the event horizon, space and time swap roles. Outside, you can move freely through space, left or right, up or down, and you can only move forward in time. Inside a black hole, the center becomes your future, as fixed and unavoidable as next Tuesday. You fall toward it the way you fall toward tomorrow, unable to steer away, because it lies ahead of you in time rather than in some direction in space. So already, near a black hole, our neat separation of space and time bends and blurs. Push all the way to the singularity, and physicists believe it shatters completely. At that point, the fabric we have been describing, the woven quantum threads that build space, gets crushed so hard that the weaving comes undone. Distance may lose all meaning, moments may stop flowing in order, before and after may blur together. The concepts break, along with the math. This is the true frontier, the place where our best theories all fall silent at once. Einstein's gravity breaks there. Quantum physics on its own cannot describe it either. To say anything real about the center, we would need the finished theory that marries the two, the theory of quantum gravity that physicists have chased for 100 years and have yet to catch. Picture a map of the ocean, detailed and reliable, marked with every current and depth. Then, at one spot, the map simply stops, and the paper is blank, with 3 words written at the edge. Here be dragons. The singularity is that blank spot on our map of reality. We can sail right up to its border with confidence, and then our charts give out, and we genuinely do not know what lies beyond. Some physicists suspect the singularity is a mirage, created by using the wrong rulebook. In this view, a complete theory of quantum gravity would smooth the point away, replacing the infinite crush with something finite and strange, but describable. The dragons would turn out to be ordinary animals we simply had not learned to see. Others think something truly new and wild waits there, unlike anything in our experience. Either way, the lesson is humbling. Inside every black hole sits a place where the two greatest theories in science both throw up their hands, a spot in our own universe, only miles away from a horizon we can photograph, where we do not know what space is, what time is, or whether those words mean anything at all. And this is exactly why black holes have become the most important objects in theoretical physics. They are the one place where nature forces the two rulebooks to meet, argue, and demand a truce. To understand a black hole's heart, we have to finish the theory that would explain everything. For 100 years, physicists have chased a single dream, one theory that explains everything, from the tiniest particle to the largest galaxy, with gravity and quantum physics finally speaking the same language. Black holes may be the doorway to it. That dream has a name, a theory of everything. It would be one master rulebook, uniting the physics of the huge and the physics of the tiny into a single set of laws with no contradictions. For most of the last century, the search felt stuck because the two rulebooks almost never met, so there was nowhere to test how they should combine. Black holes changed that. They are the one arena where gravity and quantum physics are both forced to speak at once, loudly, in the same tiny space. Every paradox we have walked through, the glowing radiation, the lost and rescued information, the firewall, the islands, came from making the two rulebooks share a black hole. Each paradox is a clue, a place where the seams show, telling physicists something about how the final theory must work. And the clues have been paying off. The holographic principle, the discovery that a three-dimensional world can be written on a flat surface, came from studying black holes. The stunning idea that entanglement builds space came from black holes. The proof that information escapes, drawn from ghostly wormholes in the math, came from black holes. Step, by staring into these dark objects, physicists have pulled out piece after piece of what the unified theory might look like. Think of a black hole as a keyhole. On this side sits everything we know, our familiar physics of stars and atoms. On the far side lies the complete theory, the master rulebook we cannot yet read. The black hole is the narrow opening between them, the one place where a little light leaks through from the other side. By pressing our eye to that keyhole and studying every glimmer, we slowly learn the shape of the room beyond. This is why black holes have moved to the very centre of physics. They have grown from exotic objects out in space, curiosities for astronomers, into the sharpest tool we have for probing the deepest laws of reality. A black hole is a natural experiment that nature runs for us, smashing the two rulebooks together in a way no laboratory on Earth ever could. Some physicists now believe that whoever fully understands black holes will, in the process, have written the theory of everything. The two goals may be the same goal: to explain what happens at the centre of a black hole, and how information escapes it, and how its interior is built. You would need every piece of the unified theory in hand. Solve the black hole, and you may have solved the universe. We are not there yet. The final rulebook remains unwritten, and honest physicists admit how far the road still runs. But the progress of the last few decades has been dizzying, and almost all of it flows from these dark, silent objects that once seemed like nothing more than cosmic drains. Which brings us back to the single strangest thread running through this whole story. Again and again, the deepest answers pointed to the same shocking possibility, one that reaches far beyond black holes and touches everything, including you. The possibility that the solid world you live in is a projection, and that reality itself is a hologram. We end with the biggest question of all, the one that has been shadowing us the whole way. Is reality a hologram? Is the solid, three-dimensional world around you a projection thrown up from information stored on a distant surface? Follow the thread we have pulled through this entire journey. A black hole stores its information on its two-dimensional surface, not its volume. A whole make-believe universe was proven to live on its flat boundary. every event inside matching something on the edge. Space itself, we saw, may be woven from quantum entanglement, built rather than given. Piece by piece, the evidence kept pointing one direction. What looks solid and deep might be a projection from something flatter and more basic underneath. If that is true for the universe as a whole, the consequences are staggering. It would mean the depth you see is a kind of grand illusion. The distance across your room, the space between you and the stars, the three-dimensional solidity of your own body, all of it could be encoded as information on a surface unimaginably far away, at the very edge of everything. You would be, in the deepest sense, a pattern painted on a distant boundary, experiencing yourself as solid and full. Now for the honest truth, because this story has earned it. We do not know if our universe is a hologram. The holographic principle is proven in special model universes, the carefully built ones physicists use for their math. Whether our actual universe, the real one holding you and every galaxy, works the same way is still an open question. It is one of the great unsolved mysteries of physics, and the smartest people alive are still chasing it. But here is what we can say for certain, and it is astonishing enough. Everything that fell into this idea came from taking black holes seriously. These objects, once dismissed as simple pits where things vanish, turned out to be the deepest keyholes in the cosmos. By studying them, physicists learned that information is never truly lost, that space may be woven from entanglement, that the two great rulebooks can be joined, and that reality might be a projection. Look up at the night sky and think about what is out there. Scattered across the darkness sit these black holes, silent and invisible, each one a place where gravity has won and light has surrendered. For most of history we saw them as endings, as the ultimate destroyers. Now we know they are something else. They are the greatest teachers the universe has, holding in their dark hearts the answers to what space is, what time is, and what reality is truly made of. The journey started with a dying star collapsing into a point of no return. It ends with a question about whether the whole world is a shimmering projection of information. Between those two ideas lies the strangest and most beautiful frontier in all of science, and we have only just begun to explore it. The black holes are still out there, still glowing faintly, still holding their secrets. And somewhere in that faint glow, in the information leaking out into the dark, may hide the deepest truth of all. That the universe you think is solid is a story written on a distant edge, and you're one of its most wondrous lines.